Welcome to today's session on model validation using real-world comparisons, an essential topic for understanding how to assess the reliability and robustness of AI models. Throughout this lesson, we will explore external validation, a critical process for ensuring that AI models can perform accurately in real-world scenarios. By the end of this session, you will have a thorough understanding of how external validation works, its importance, and the steps involved in implementing it effectively. Let's start with the lesson objectives to frame what we aim to achieve today. First, you will learn to define external validation and its role in AI model assessment. Understanding this foundation is crucial for recognizing how real-world comparisons can strengthen AI performance. Next, you will learn to identify real-world datasets that can be used for validation, ensuring that the datasets are relevant and meaningful for your AI model. You will also gain the ability to compare AI predictions with actual data using statistical validation metrics. Finally, we will focus on analyzing discrepancies between predictions and real data, discussing how to improve models based on these insights. Now that we've established the objectives, let's dive into the key concepts, beginning with the question, what is external validation? External validation is the process of comparing AI predictions with independent, real-world data that the model has not encountered before. This step is fundamental because it ensures that the model is not simply memorizing the training data, a problem known as overfitting, but is genuinely learning patterns that generalize well to unseen scenarios. For instance, imagine an AI model designed to predict public transportation demand. During validation, the model's predictions can be compared against real data from an AI bus trial to assess its performance. If the predictions closely match the real-world data, it indicates that the model is robust and reliable. Now, why is external validation so important? There are three key reasons. First, it helps to prevent model bias and overfitting. A model that performs well on its training data but fails when faced with new data is essentially useless in practical applications. External validation ensures that the model is tested against independent datasets, highlighting its ability to generalize. Second, external validation strengthens trust in AI-based decision-making. In policymaking and other fields where decisions have significant societal impacts, stakeholders need to be confident that AI models produce accurate and reliable results. Third, external validation enhances data-driven policy formulation. Validated models provide policymakers with actionable insights that they can use with confidence to develop effective and evidence-based strategies. Having established what external validation is and why it is important, let us now explore the steps for implementing external validation. The process can be broken down into three key steps. The first step is to select a real-world dataset. This step involves identifying relevant data that aligns with the AI model's predictions. For instance, if your model predicts transportation demand, you could use public transportation ridership data as your validation dataset. The dataset should ideally be independent of the training data to ensure that the validation results are meaningful. It can be sourced from publicly available databases or proprietary systems, depending on the specific use case. The second step is to compare AI predictions with real data using appropriate validation metrics. This involves calculating statistical measures to quantify how closely the model's predictions align with the actual data. Common metrics include mean absolute error (MAE), root mean squared error (RMSE), and R-squared. Mean absolute error measures the average magnitude of errors in a set of predictions without considering their direction, making it a straightforward and interpretable metric. Root mean squared error, on the other hand, places greater emphasis on larger errors, making it useful in scenarios where significant prediction inaccuracies are especially problematic. R-squared, or the coefficient of determination, measures the proportion of variance in the real data that is explained by the model's predictions, providing a clear indication of how well the model fits the data. The third and final step is to analyze discrepancies and improve the model. Once the comparison is complete, it is crucial to investigate any differences between the predictions and the real-world data. These discrepancies could arise from various factors, such as missing features in the training data, limitations in the model's architecture, or external influences not accounted for by the model. For example, an AI model predicting bus ridership may fail to account for a public event or extreme weather conditions that significantly impact demand. By identifying and understanding these discrepancies, you can adjust the model's parameters, refine its training data, or include additional variables to improve its performance. This iterative process is key to building models that are not only accurate but also robust and adaptable. In conclusion, external validation is a vital process for ensuring the reliability and robustness of AI models. By comparing model predictions with real-world data, we can identify and address weaknesses, improve model performance, and build trust in AI applications. Whether you are using AI to predict transportation demand, assess economic indicators, or analyze demographic shifts, external validation ensures that your models are not only accurate but also applicable to real-world challenges. This process empowers policymakers, decision-makers, and stakeholders to make informed choices, ultimately leading to better outcomes for society. Thank you for your attention.